Does anyone have any questions? Okay, let's get to the lab. So this lab, you didn't have a lot of time to read up on it. So I'm going to take a fair amount of time explaining to you what mass spectrometry is, okay? So we're going to be looking at mass spectrometry, and first I'm going to change my share screen to the lab itself. So I'm going to go to my web browser, and you can see I have the lab right here. So let's take a look at the lab. You can see that in the lab notebook, you're going to have an intro, safety, and then you're going to have what looks like a procedure, data, calculations, hypothesis, accepted results section. That's going to be a little weird because it's a mixed jumble. And then you're going to follow it all up with a discussion. And you're going to submit photos of different things as you accomplish them. So you should have your lab notebook with you right now. And we're going to go ahead and get started. And on the first page of your lab notebook for this one, you should write at the title, the very top, mass spectrometry. So that you know how to spell it, there it is on the screen. So there's a lot to read here, but I'm going to kind of summarize what I would put in the introduction for mass spectrometry. And you've probably heard already that for the introduction, I like bullet points. I don't like to write paragraphs. But one of the things that we're going to learn about mass spectrometry is that it's good for determining information about elements and molecules. What information is it good for determining? Well, for elements, I'd say mass spectrometry. I like to abbreviate mass spectrometry as MS. So MS is good for determining the mass of different isotopes and their relative amounts. So what I need to know now is, are we okay with the idea of isotopes? If not, I need to do a real quick description of isotopes. Are you okay, Charlotte and Gabe, with isotopes?
Yeah.
How about you, Gabe? You okay with it?
I'm new, but I think I have the understanding is that it is, I mean, the definition is atoms with the same atomic number, but different atomic masses.
Right. So you're going to need a brief description. So we're going to do that. Okay. I hope you don't mind. So I'm going to change my share to this. So we're going to look at isotopes, and I'm going to draw for you 3 isotopes of hydrogen. So one isotope of hydrogen, actually, yeah, I'll do hydrogen. One isotope of hydrogen has a proton in the nucleus, and it has 1 electron. This one's called H11. Another one has 1 proton in the nucleus, 1 neutron in the nucleus. Same size, although I'm not very good at doing that. And this is called H21. And then there's one with 1 proton and 2 neutrons. Same size, 1 electron. And this is H31. So these are all isotopes of hydrogen. So what are the things that we notice about isotopes? They have the same number of protons. We also notice that for these neutral atoms, the number of electrons equals the number of protons. 1, 1, 1, 1, 1, 1. And that they have a different number of neutrons. Here you have 0, here you have 1, here you have 2. And they have different masses. Now, the other thing you need to know about these nuclear particles is that a proton weighs 1.00 AMU approximately, and a neutron weighs 1.00 AMU approximately, and an electron weighs 0.00 AMU approximately. So how much does this guy weigh? 2.00 AMU. This guy weighs 1.00 AMU and 3.00 AMU. So they weigh different amounts. Now, this symbol here, we're going to take a close look at these. Try and get rid of that shadow there. So if we look at H11, this is called the mass number, and it's equal to the number of nucleons. And a nucleon is simply a particle in the nucleus. This is called the atomic number, and it's equal to the number of protons. So in your nucleus, if you can only have protons and neutrons, and you've only got one of them, and you know that it happens to be a proton, that means there's no neutrons. And so you can do a little subtraction here, and you get 0 neutrons. You can do the same thing for this isotope of hydrogen. You got 2 nucleons, 1 proton, do a little subtraction, and you get 1 neutron. Now, remember, each nucleon weighs 1.00, so overall, this guy weighs 2, this guy weighs 1. So that's a quick little overview of isotopes. And the other thing I'm going to tell you very quickly is that for these 3 isotopes, there is another way to write them. You can write it like this or like this. They all mean the same thing. For this one, it would be this or this or this. Any of these 3 are fine. And in general, when we write it this way, that's the mass number. That's the atomic number. And that's the symbol of the element. And if you're as bothered as I am, you don't like A being mass number when it seems like it should be atomic number. Go figure. That's the way it is. Now, the reason this is called mass number is because really it's the number of nucleons, but each nucleon weighs 1, so it's also the mass. Okay, so that's a very quick overview of isotopes. And the last thing I'll tell you is that when you look at these 3 isotopes, H1, H2, and H3, you might expect them to be 33%, 33%, and 33%. And that's not the case. Rarely are isotopes equally abundant. In fact, this is like 99.9985%. And this is like 0.0015%, and this is 0%. So this is exceedingly rare. 0 doesn't mean there's not any of it. It just means that to the number of significant figures we have here, there aren't going to be any. Okay, so those are isotopes. Now, mass spectrometry is good for finding out the mass of isotopes and how many of each for an element. So my introduction would say mass spectrometry is good for finding out the mass of each isotope and its relative abundance. So that's all going to go in the introduction. And I'm going to show you something from your book and describe it to you. And you probably want to put a little bit of this in the introduction. I'm going to zoom in on this. So this is a cartoon of a mass spectrometer. You can see, looking at the figure, that there are different sections of the mass spectrometer. There's the vaporization section, ionization section, acceleration section, deflection section, detection section, and then this is the analysis. This is the output. So let's first talk about vaporization. When you submit a compound to mass spectrometry, you need to turn it into a gas. So if you have something that doesn't want to melt, it certainly doesn't want to turn into gas. And the way to make that happen is to use high heat or maybe a laser. But you turn the particle into a gas. And that gas particle will move around in this chamber, and it's going to go through that little hole there, which is part of the something called a repeller, which has a positive charge. So here we're looking at neon atoms, and there are three isotopes of neon. They are neon 20, 21, and 22. Okay. So when a gas particle gets through here to the electron gun, here's what happens. So I'm going to draw that for you. So here you have a neon 20, and the neon 20 has 10 protons, 10 neutrons, because 20 minus 10 is 10. That's the nucleus. And then it's got 10 electrons. Oh, I shouldn't have done that because I don't want to draw 10 electrons. I guess I'm forced to now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, I'm going to change that drawing and call this my electron gun. And it's shooting electrons at this atom. And you can't see this because I've got my screen too large here now for what I'm drawing. So here's my electron gun, which is shooting an electron. And that electron is going to take one of these electrons, and both of these are going to end up going to the electron trap. So what's going to happen to this guy is it's going to end up having 10 protons, 10 neutrons, and only 9 electrons. Now, this thing here, because it has more protons than electrons, it has a positive 1 charge, and we would write that symbol like this. Still has 20 nucleons. It's still neon because it's got 10 protons, but has a positive 1 charge. It's a cation. And hopefully you've read that part about cations. They have a positive charge. Like charges attract, like charges repel, opposites attract. So let's go back to this guy right here. And see what happens when you form a cation. Trying to get the right size for what I want. So let's see what happens when you form a cation right here where it says ionization. So you've got a cation with a positive charge. It's repelled by the repeller plate because that's got a positive charge, but it's attracted to these accelerating plates because they have a negative charge. So what happens to that ion is it is attracted to the accelerating plates, and most of the cations that form are going to hit the accelerating plate, get an electron, and become neutral again. A few of them will go right through the accelerating plates and get past and get to this magnet. And here, the magnet is used to deflect the flight path of the ion so that it can hit the detector. What's cool about this magnet is that you can adjust the magnet so different masses will hit the detector. So you can tune this magnet so only the 20s hit because they weigh 20. You can tune the magnet so the 21s hit because they weigh 21. And you can tune the magnet so the 22s hit because they weigh 22. Turns out that the flight path of these different ions are different because they weigh a different amount. And you can use the magnet to actually adjust the flight path. So here's how you get the mass of each of these ions. You tune the magnet for a particular mass. And if an ion hits, it has that mass. Furthermore, you tune the magnet for 20 for 10 seconds, then 21 for 10 seconds, then 22 for 10 seconds. And you might get that 5 million 20s hit in those 10 seconds. And you might get that, let's see, I said 5 million. You get 25,000 21s hit in 10 seconds. And then you get 50,000 22s hit in 10 seconds. That's the kind of data that you plot. So by leaving the detector on for the same amount of time for each different mass, you get the relative amount of each. So let's take a look at that example where I said you get 5 million of the 21s or 20s. And let me think about that. It's actually going to be 5 million of the 21s, or 5 million of the 20s. And you get, we're going to say 500,000 of the 21s, and we're going to say 250,000 of the 22s. So when we plot these, you want to plot the hits over here and the mass to charge over here. Now remember, each of these have a charge of +1, and this has a mass of 20, this has a mass of 21, and this has a mass of 22. So 20 divided by 1 is 20. So you've got 20, 21s, and 22s. So if I plot this as 5 million, where does 500,000 go? Oh, and I messed these up. We're going to make this 250,000 and this 500,000. So 500,000 would be about 1/10 as tall as this guy. You guys follow? And how big would 250 be? It'd be half as tall as that guy. But when you look at a mass spectrometer, this is not the data it actually reports. It would report this instead, intensity. This would be given a 100. This would be given a 2.5. Or excuse me, this would be given a 5, and this would be given a 10. They report numbers like that. And what this means is that your biggest peak is arbitrarily given the value of 100, and every other peak is proportional to that. Because when you're plotting this data, you don't want to work with numbers like 5 million, and it's not going to be 5 million. It's going to be like 5,624,321 million. And this is going to be 562,416. And this one's going to be 281,122. Those are the real numbers you're going to get. And it gets messy. So you take this data and turn it into this, and you arbitrarily set that guy to 100. So that's the real data you get. Now, if you take a look at what the book gives you, it actually gives you about 90 for the 20. It gives you about, 4 for the 21. And it gives you about 8 for the 22. These are percentages. And when you add them all up, so if we get 90, actually I'm going to call this 88 for an 8%, you add these all up, you get 100%. So that's what data we see here. This is manipulated data so that you have percentages. Okay, so back to the intro, I'd say that the introduction is going to tell you the relative amounts of each isotope and how much each one weighs. That's what mass spectrometry is going to do. Okay, let's move on and go back to the lab. Now, if you didn't finish the introduction, leave a little space so that you can finish it, and go ahead and write this part down next. I'm skipping down. You see the safety? You want to write that into your lab notebook. Safety, there are no safety issues with this lab. The only real safety issue with this lab is that it is a very intensive lab for thinking. And so you may want to, poke your eye out with a pencil. There's going to be a lot of thinking here in the next hour. Okay, so that's the safety. Now let's get on to the procedure. So here's the procedure. Do each of the following step by step. Do not look ahead. So you can write this into your lab notebook as we do it. And remember, your lab notebook doesn't need to be perfect. You just make it as neat as you can as you go along. So we're going to write procedure, data, results, calculations, and we're going to write step 1. You don't need to write down these steps, but you can if you want. We're going to go to Web Elements and link to bromine. Scroll down until you find the bromine isotopes and a plot. Find this link, copy down the table, the masses, and the plot. And then it goes on to explain that the signals are from the mass spectrometer, and we'll see what the plot looks like. So let's take a look here at Web Elements. And I'm going to go back to the Web Elements where you just see the periodic table. So here's Web Elements, the periodic table. I'm going to link to bromine. And you can see that it says bromine, the essentials. And if we scroll down, you see physical properties, heat properties, electronegativities, and so forth. We're going to keep scrolling. And eventually you're going to get to a place where you see bromine isotopes and a plot or a spectrum. Do you see the link down below here that says more isotope and NMR data? You see that?
Yep.
We're going to link to that. And here is that table I was talking about where you want to copy down information. So in your lab notebook, you want to write down this information. We're going to do it together. So you see all these numbers here? So
Yeah.
Let me show you what we're going to write down. So I'm going to have to switch screens, okay?
Okay.
So for bromine, this is what your data table is going to look like. First of all, you'd like to list your isotopes. So we've got bromine 79
So
and
this
bromine
section goes
81.
in your data.
This is part of step 1, and this is data from step 1. So the procedure is go to Web Elements and look up the data table and the mass spectrum for bromine. That's the procedure if you want to write that down.
Yeah.
And so here's the data table. The isotope is bromine 79 and bromine 81. The mass in atomic mass units is 79 and 81. We're going to put 79.0 and 81. Actually, we're going to write 79 and 81 because I believe in the lab instructions, I say, write down the mass, but round to the ones. So they give you, 78.9, blah, 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 blah. What does this round to when you round to the ones? 79. And then you're going to put the percent or natural abundance. And there's a 50.69 and a 49.31. So that's your data table. And then you're going to write the spectrum down. And this is going to say intensity. And this is going to say percentage. We've got a signal at 79 for bromine 79 and one at 81. And this is the mass to charge ratio. Now, On the drawing, this says 150.69. And this says 97.28 and 49.31. So once you have this written down, give me a little thumbs up, and we'll go back to the website so we can see that this is what they have on that website. And again, the cool thing about you having called in is if you're writing this up in your lab notebook right now, you don't need to do it later.
Mhm.
And you have me walking you through it. Are you good to go, Gabe?
My thumbs up not coming through.
No. Find your participant list. Can you find that? I think you're using the thumb where you see it in the window. I don't have the window open. I have the participant list open.
I see.
And the reason I don't have your window open is because I would have 3 screens to look at and it's too hard. But if you open your participant list, you see the choices on the bottom?
Yeah.
One of them might be a thumbs up or a yes. That's all I'm looking for. Give it a shot and see what they're perfect. Perfect.
I'm on board.
Thank you.
You're welcome.
Okay, so we're going to go back to, the lab itself. And here's web elements. So can you see how we got the 100, the 97.28, the 50.69, 49.31. On the left, it says relative intensity. I just call it intensity. On the right, it says isotope abundance percent. I just put percent. You might want to write those into your plot if you want. So are there any questions about what we're supposed to have done so far for bromine?
I don't think so.
So let's take a look at the numbers there. The numbers in blue mean that out of all the isotopes of bromine, 50.69% are bromine 79 and 49.31% are bromine 81. So mostly bromine 79s. You with me there?
Yeah.
Slightly though. Now, notice the 100 and the 97.28. Those are the actual numbers you get from the mass spectrometer, and you have to calculate 50.69 and calculate 49.31. I'm going to show you how that's calculated because it's kind of interesting. So I'm going to switch screens back to my paper. So I want to show you how you can take that 100 and the 97.28 and get 50.79. So the deal is percentage is equal to part over whole times 100%. That's how you calculate percentage. So if you have 5 brown eggs out of 10 eggs total, 5 out of 10 is 0.5 times 100, 50% of your eggs are brown. So for this peak, what do? We always say it's got an intensity of 100, but the total intensities are 197.28. We add these two numbers together and then multiply by 100%. And here we should get 5 significant figures because these 100s are defined, they're exact. And this 197.28 is 100, which is exact, plus 97.28, which is good to the 100th. So we round to the 100th. So when I do this work and do 100 times 100 and then divided by 197.28, we get 50.689%. And can you see that they rounded this to 50.69?
Yeah.
So I'd like you to do that for the other peak, where you're going to put 97.28 at the top over 197.28 times 100% and calculate the percentage. Here you only get 4 significant figures because of this 97.28. When you're done, just give me a yes. And I'm not going to put you on the spot and ask you what number you got. I just want to know you're done. So 97.28 divided by 197.28 times 100. And we get 49.31%, which is that number there. So that's how they're getting those numbers, 50.69 and 49.31. Okay, any questions about how we did that? Are we good to go? Go ahead, Gabe.
If you could just maybe just go over it just kind of one more time.
For calculating these percentages?
Yeah.
Well, the general formula is part over the whole. And so in this case, if we are more specific, we're talking about the intensity of a peak over the sum of all intensities times 100%.
The sum of all the isotopes. That's the whole. I think that's what I'm
Right.
getting the individual whole mixed up with the.
So that's
entire whole.
that's a part. That's a part, and together they make a whole.
Okay.
And if you had 3 peaks, you would have 3 parts, and altogether all 3 would be a whole.
Right.
Okay.
Got it.
All right. So that's how you take these numbers and turn them into a percentage, because this isn't really a percentage. You can't say, oh, it's 100% this and 97.28% that, because there's no such thing as 197.28%. Not really, except in football. You can put in 197.28%, you know, that's a joke. We all know they only put in 110%. That's also a joke. Neither of you are football players and offended by that, are you?
No.
Very much not.
Okay, good. But I just love those sports shows. We put it on 110%. No, you can't. The best you can do is 100. That's it. Okay, let's go back to the lab. A lot of jumping back and forth here. So here's the lab. So this shows you how we're calculating those percentages.
Does this need to go in our procedure?
Well, that's a calculation. So I put the calculation in there.
Okay, put it under the calculation section.
I'm going to go back here. So remember here how I said that this is actually going to be a procedure data calculations hypothesis accepted results section. So for this step 1, you're going to do these things in the order in which we do them. So you're going to draw the plot. You're going to, here you don't really need to do these calculations because it didn't ask you to do those calculations.
Okay.
It's just telling you how they came about. But now we're about to do some calculations. Are you ready?
Sure.
I think so.
Go ahead, Gabe. Sorry.
I said I think so. This chemistry is an extreme brain exercise.
It is. It is extreme brain
It
brain.
requires 160% of my brain.
Yeah, it's not a Who are you borrowing from? You didn't borrow the brain from Abby Normal, did you?
I got 60% of a clone done.
Abby Normal comes from that movie Young Frankenstein. If you haven't seen it with Gene Wilder, you gotta see it. It's funny as heck. All right, so let's go to the mass spectrum simulator. So I'm going to go back up towards the top here kind of slowly. And do you see the link here to the mass spectrum simulator? I call it a simulator.
Yeah.
And this is what we're going to be looking at when we open that up. And I've already linked to it right here. This is the mass spectrum simulator. And we're asked to type in bromine. So do you see the chemical formula here? I'm going to type in uppercase B, lowercase r, and hit enter. And here is the mass spectrum simulator data for bromine. Now, here in the upper right corner, do you see, or in the middle of the page, I should say, data table mass intensity?
Yep.
And the plot is below. So let's go back to the lab so that we can write the stuff into our lab notebook, because that's what we're going to do. So we're still on step 1. Go to the simulator, type bromine in, get the mass spectrum, report the data table, draw the spectrum, calculate the percentage of each isotope based on its intensity. So we're going to do all that together. I'm going to show you how to do it. And then you're going to tell me what comments you would write. So here we go. I got to change my share. Sorry about this, but it's the only way I can do this. So from the simulator, when we look at the isotopes, for bromine 79 and for bromine 81, we have the mass as 79 and 81. That's from that data table. And we have the intensities. You may not recall this, but they are 97.5 for 81 and 100. And the plot looks like this. They don't use M over Z, they use M over E, but it really means the same thing. This is intensity, and this is 100, and the 79 goes all the way to 100, and the 81 almost goes to 100. So that's what you're asked to draw from the simulator. So I'm going to give you a moment, and when you get that drawn in your lab notebook, give me a little holler. All right, give me a thumbs up. And the beautiful thing about drawing these things is you don't really need to do it perfectly. You're just trying to get the information. And these are the same bits of information, just written a little bit differently. One is more of a visual and one is a table.
Good to go here.
Excellent.
I'm ready.
Great. So now we're supposed to calculate the percentage for each peak. And I don't know if I said this before, but these lines here are called peaks, but also signals. Okay, so let's look at the peak at 79. So remember, percentage is part over whole times 100%. So for the 79 peak, this is 100 and this is 97.5. The part is 100. What's the whole?
197.5.
197.5 times 100%. And let's see what we get. We get 4 significant figures because of the 197.5.
Didn't we just do this?
We did, but let's see what we get.
Okay, I'm confused.
I get 5.63%. Now let's do the 81. And when you're done, just give me a thumbs up like you've got an answer. How many significant figures do we get for this second calculation?
3.
3 because of the 97.5. I get 49.4%. Now, the next part of this step 1 says, look at these numbers and compare them to what we got here. So here's the numbers we calculated here, and let's write them down and compare the two. So this is the simulator, and this is from Web Elements. What do we think of these values? Are they precisely the same?
Pretty close.
Pretty darn close. And that's what I would say in my comment is that, you know what? These are pretty darn close to one another. And if anything, the reason they're not is because the web intensities were 197.28. That's why they differ a little bit. So you're right, Charlotte, and it seemed like we just did this, but we did it with the numbers that were slightly different. Capiche?
Okay, hold on. Don't move on yet.
Don't do what? Don't do this?
Don't move on yet.
Does it help if I do this?
No. I'm looking at my own paper anyways.
Oh, okay. Okay, the next thing I'm going to do in a bit here is I'm going to make you do a little thinking. And you can do this on a piece of scrap paper. It doesn't need to go in your lab notebook, but I want you to think about this, okay? Actually, the next one needs to go in your lab notebook. I'm wrong. So tell me when you're ready to go on.
Are we moving on to step 2 now?
We are.
Okay, hold on.
And for your comment, you don't need to write it right now. You can always leave just a little space and put a little comment later, because you do want me to help you explain these steps as we go through them.
Good to go.
Okay. I don't know about you guys, but it's sunny outside right now.
Yeah,
Right.
looks nice. Partly cloudy, but a little sunny. I'm in Arcata.
Ah, here in Eureka, it's sunny. I'm by Sequoia Park. All right, you good, Charlotte?
Yeah.
Okay, let's go to step 2. I'm going to do a switch screen. And here's step 2. There are 2 isotopes of boron, boron 10 and boron 11. That's how you'd say that. The atomic weight of boron is 10.81 AMU. So that means the average weight of a boron atom. Based on this information, draw a qualitative plot of the mass spectrum of boron. Remember to make the largest peak 100 and draw the other peak proportionally shorter based on your intuitive guess, based on the information provided. So I want you to take a moment here and help me out with a few questions. How much does boron 10 weigh?
10 AMU.
10 AMU. Because that number at the top is how many nucleons. And since each nucleon weighs 1, 10 times 1 is 10. How much does boron 11 weigh?
11 AMU.
That's right. Now, if we had an equal distribution of those isotopes, 50% of each, what would the average boron atom weigh?
10.5 AMU.
10.5 AMU. Suppose there were more boron 10s than 11s, like say maybe, 90% 10s and 10% 11s. What would the average be closer to?
10 AMU.
10.
10, right. And if there were 1 10 for every 10 11s, so 1 boron 10 for every 10 boron 11s, what would the mass be closer to?
11 AMU.
11 AMU, because you've got more 11s. You with me?
Even though the 11s weigh less.
No, the 11s weigh 11, the 10s weigh 10.
Okay.
So if you have let's say we have 9 boron 11s and only 1 boron 10, wouldn't you say the average should be closer to 11?
Yes.
And the 11s weigh more.
Okay.
Okay, so with that in mind, which isotope do you think is more abundant, knowing that the average weight is 10.81? 10 or 11?
11.
Boron 11.
The 11. So which peak is going to get the 100%?
Boron 11.
Boron 11. So now let's take a look. I'm going to switch screens. And this is what we're going to do. We're going to draw a hypothetical mass spectrum, our intuitive guess. So I'm going to change my share to my paper here. So we want to do this. We're going to say boron. We're going to put intensity here. We're going to put 10 and 11, and we're going to put M over Z, and we'll make this 100. So what are you going to draw as the first thing for your spectrum?
100 on 11.
That's what I do. Now, what are you going to do for your 10? This is your intuitive guess. So go ahead and draw this into your lab notebook. And the beautiful thing about this is your guess may be wrong, and that's okay. But if you don't guess, you're graded as it being wrong. So put this into your lab notebook. if you make a guess, you're right, even if your guess is wrong. Tell me when you're done.
Would 10 be like a quarter of the?
It's your ball game here, Gabe. So you just make a choice. Your intuitive guess and draw it.
I'm going with a quarter.
Okay. How about you, Charlotte? Are you done?
Yeah.
Okay, so I'm going to write down two guesses. So here's one guess, and here's the other guess. Okay. So clearly both of these are shorter than that one. One is a lot shorter and one's a little more than halfway of this one. These are the two guesses. Capiche? Now we're supposed to go to web elements, or we're supposed to go to the simulator and find out what's going on. So this is the test. We're testing our hypothesis. So I'm going to type in boron and enter, and let's see what it looks like. So take a look. It looks like the 10 is about a quarter of the length of the 11, doesn't it?
It does.
So I'm going to change my screen, and you want to go ahead and write this down. And I'm going to go up just a little bit. Do you see the data here? The 11 is 100 and the 10 is 24.7, which is actually a quarter. 25% of it.
Mm-hmm.
So go ahead and draw this, and you can write the numbers in 124.7. And now let's go to the comment area, because that's the next thing you're going to do for this step 2. You're going to write a comment. So I'm going to switch back to the lab. And it says, compare your hypothesis with the accepted plot. What did you do well and not so well? Now I'm going to switch my screen. And we're going to take a look at this one right here, and we're going to look at the green guess. The green guess. What did we do well?
Kept it below the value of 11.
I would even go back a step and say, you know what? We got a peak at 10 and one at 11. And so did the generator or the simulator, right? So we want to go to the fundamentals. We got the 10 and the 11 correct. Our 11 was 100 intensity. And so was the simulator. And so that's good. That's good. And this remark kind of covers that the 10 was shorter than the 11, Gabe, okay?
Okay.
And then the thing that we didn't do so well is that the 10 was too tall. Okay? So for the blue, how would we evaluate the blue? Well, we'd say we got the peak at 10 and we got the peak at 11. That's great. The 11 was the 100. And here, the 10 was close to the same as the simulator. And we would say the intensity. So we did 3 out of 3 things right if we went with the blue. And the beautiful thing is, it doesn't matter which one you picked. It doesn't matter which one you chose. If you chose the green one, this is what you would write. And if you chose the blue one, this is what you would write. And that's the way science works. If you're guess doesn't work out, you analyze it and you say, well, this didn't work out. Now, what would we do in addition to this? We try to figure out, well, why was my guess too high there? Okay. So any questions about step 2? Okay, we're going to move on. Let's go to step 3. So I got to go back to my browser. Step 3. There are 7 elements that are found as diatomic molecules, 2 atoms bonded together. Hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. If you look at those symbols, HON is Han, Cl is coal, and BRIF is brief. So a lot of people remember these 7 elements as Hunkelbrief. So these elements, when you buy it in a jar, the atoms are bonded together, stuck together like Siamese twins. One way to remember these 7 elements instead of Hunkelbrief is have no fear of ice cold beer. So elemental bromine is actually Br2 and not Br. Br we would call atomic bromine because that's an atom of bromine. When elemental bromine is subjected to mass spectrometry, it is ionized but not fragmented. So before we move on, I want to draw a picture for you. So I got to switch screens. So do you remember that mass spectrometer where you have an atom? It goes through the electron gun. And after it comes out of the electron gun, it's an ion. And then it goes eventually to the detector. And the detector measures the mass and the intensity. So this is what's happening with a bromine atom. Now, what happens if you have 2 bromines stuck together? Well, it goes through your electron gun. They stay together. And then they go to the detector together. And you get the mass and you get the intensity. So, what is the mass of 2 bromines going to be compared to the mass of 1 bromine?
Double?
Double. That's it. Okay, so let's go back to the question or the step 3. So this is going to take some thinking on your part. There are 2 isotopes of bromine, 79 and 81. And you might remember that we looked at these earlier in step 1, right? We looked at the isotopes of bromine. One was 100 and the other was 97.5.
Mm-hmm.
Okay, so based on this idea, let's see. Based on this idea that you have 2 bromines, 79 Br and 81 Br, and this one is 100 and this one's 97.5, I want you to draw the mass spectrum for Br2. This is going to be intensity, and this is going to be the mass to charge ratio. So you got to figure out what masses you're going to put here and how tall the peaks are going to be, gut feeling. So go ahead and work on that. And when you have something, give me a little indication like, yeah, I've got it, or give me a thumbs up. Usually in class, during lab, there are 3 people sitting side by side at a bench. And I make the 3 people work together and discuss their ideas. Why do you think I do that?
'Cause 3 brains are better than 1.
Usually they are. And also to mimic how science is done. Scientists don't work alone. They talk with their colleagues. Unless
So
you're young Frankenstein, he is working by himself.
I'd initially think that it would be twice, but I'm kind of confused on how to go
When you say twice,
double.
what do you mean?
Well, like you said, the difference between the bromine and the bromine 2 is that the bromine 2 has double the mass.
Double the mass.
So then
Hmm.
I'm just trying to figure out how to double the 100.
No, that's the intensity. That's
That's
not
the
the
intent.
mass.
Okay, so you would just double the 79 and the 81.
Okay, so go ahead and double those. What do you get?
148 and 162.
One
158.
58 and 162,
Yeah.
like that. Which one is going to be bigger?
The 158.
What do you think, Charlotte? Will the 158 be larger?
Yeah,
Why?
because the intensity is 100.
Yeah, when you have 2 100s compared to 2 97.5s, this should be taller. So we're going to do that and we'll make that one shorter. Does that look good?
Mm-hmm.
Yeah.
That's your hypothesis. What's wrong with this hypothesis?
Hasn't been tested.
Hasn't been tested, which means there's nothing wrong with it. It just is not through the process yet. This is a beautiful hypothesis. We have an explanation for why. We could even draw it, right? This is a bromine 79 bonded to a bromine 79, and that's why it weighs 158. Are you with me there?
Mm-hmm.
Beautiful hypothesis. Fantastic. So you should write that in your lab notebook and take a photo of it before we move on. And the reason I'm having you do this is because if we're right, great. But if we're wrong, let's learn something. And in science, you have to be willing to be wrong and learn from it. But you also have to be willing to be right. So tell me when you guys are ready to go on. Is someone unwrapping a candy bar? Is that what I hear?
It might be my arm on the book.
Oh, maybe it was just my suggestive mind thinking it was a candy bar.
You have low blood sugar?
No, not really. I just had a sandwich, so I'm good. But I love candy, chocolate especially.
I'm in that boat too.
Yeah, chocolate is lovely.
I'm good to go here.
Okay. Charlotte, you good to go?
Yeah.
Okay. Let's go back to my what do you call it? Web browser. So here, take a photo of your plot. before proceeding. Now we test the hypothesis, report the data table and the plot, and evaluate. So I'm going to go to the mass spectrum generator, the simulator. I'm going to type BR2, and you'll notice here that I can't write a subscript. So you just write the 2 as a normal letter or character, and we hit enter. And look at what we get. The data table says 158, 160, and 162. And the 160 is actually the tallest. What gives? Huh. Where does the 160 come from?
Yeah.
We know the 158 is a 79 and a 79, correct?
Is it a mixture of the two?
Oh, what's 79 plus 81?
160.
Oh, it's probably a mixture of the two. We didn't think of that. So did we learn something?
Yes.
Another isotope?
Yeah, we learned that isotopes don't really care who they partner with. They'll partner with an isotope that's just like them or an isotope that's unlike them. Isotopes are not isotopist. You with me?
Mm-hmm.
Well, wouldn't you expect that the 158 would be the tallest, the 160 would be a little shorter, and the 162 shorter yet? Because the 160 is made out of an 81 and a 79. So one that's pretty abundant and one that's slightly less. Wouldn't you expect 160 to be taller than 162?
Does it have to do with the charges and the opposites attracting, and so that makes the 160 more?
Absolutely not. So let's figure out why. Take a look at step 4. Here's the explanation. Have you guys ever heard of a Punnett square from Mendelian genetics?
Yes. Never done one, but I've heard of one.
Well, this is a Punnett square. And basically, you have these two genotypes, G and little g, big G, little g. And so these are your two parents, F1 and F1. From one parent, you can have big G, little g. From the other parent, you can have big G or little g. When they make offspring, you could get a big G, little g, big G, little g, or little g. And from these parents, you will have a 25% likelihood of any one of these occurrences. So if you look at these at being 25% each, can you see that the G, little g, big G, when you add those together, that's 50%. So if we were to plot that, and I'm going to do a switch screen here. So little g is 25%, big G is 25%, and little g, big G is 50%. If we were to plot that, it would look like this. So I'm going to change that. Big G, 25%, big G, 50%, and little g, 25%. So in this class, we do something called Tony square instead of a Punnett square. It's not catching on across the nation. Chemistry classes aren't calling it Tony square everywhere, but maybe someday. So here's Tony square. You could have a bromine 79 or a bromine 81. And remember, the bromine 79 is a 100 and the 81 is a 97.5. And here's Tony square. Or you could have here a bromine 79, a bromine 81. This is a 100, and this is a 97.5. So what is the mass to charge going to be if you have a 79 and a 79? 158. What's the mass charge going to be if you have a 79 and an 81? 160. What is the mass going to be if you have an 81 and a 79? 160. And an 81 and an 81? 162. So that's the beginning of our Tony square. And to find out the likelihood of each one of these, what we do is we multiply these numbers together and divide by 100. So this is going to be a relative intensity. So our mass to charge ratio of 158 is going to have an intensity of 100. What's 97.5 times 100 over 100? $97.5. Here we're going to have 100 times 97.5 over 100, which is again 97.5. And this last one, we're going to have 97.5 times 97.5 over 100, which gives us 95.1. So our mass to charge of 162 is going to have an intensity of 95.1. But our mass to charge ratio of 160, you've got a 97.5 and another 97.5. When you add them together, you get 195.0. So if we were to plot this, 158, 160, and 162, and we call this 195, there's your 160, there's your 100, and there's your 95.1. Now, how do we make this look like the mass spectrum generator? So right now, this is 100, this is 195.0, and this is 95.1. How do we make it look like that peaks 100? Well, I'm going to show you how to make that peak turn into 100. Are you guys ready for that?
Yeah.
So
Yes.
I want to make that peak into 100. So I'm going to take 195. I'm going to divide by 195, and I'm going to multiply by 100, and now it's 100. I know it sounds really simple. I'm going to divide by 195 and multiply 100, and I get 100. Are you with me there or not?
Yeah, that's just like a canceling kind of thing, right?
Absolutely. But do you remember algebra says that whatever you do to one thing, you got to do to the others to keep everything equal?
Right.
What do I got to do to that 100?
Divide it.
Divided by what?
195.
195 and multiply by what?
100.
100. So let's see what that turns into. 100 divided by 195.0 times 100 and see what we get. I get 51.28. Anyone else? Oh, my internet connection is unstable. That's no good. What is this number going to be?
Do we do 100 divided by 95.1?
Nope, you do 95.1 divided by 195.0 times 100. So this is the thing that you're doing each time. Since the first peak, the tallest, we divided by 195, you have to divide them all by 195. And for the first peak, since we multiply by 100, you have to multiply them all by 100, okay?
Okay.
So I get 100, I get 51.28, and I get 48.8. And guess what we're going to do now? We're going to look at the mass spectrum simulator and see what numbers they got. So I'm going to change my share screen back to the web browser. I'm going to go to the simulator. And you see those three peaks at 158, 160, and 162?
Yeah.
Let's take a look at the numbers. 51.3, we got 51.28. Are they the same pretty much?
Pretty much.
Is 160, we got 100, they got 100. 162, we got 48.8, and they got 48.8. So that's the explanation for why the 160 is twice as tall as the others. It turns out that there are two ways of getting 160. You can have a 7981 or an 8179. The order matters. But there's only one way of getting a 158. That's a 7979. And there's only one way of getting a 162. That's an 8181. Capiche?
Makes sense.
So how do we analyze our hypothesis? We would say, you know what? We got the 158. We got the 162. Our 158 was slightly taller than the 162, so we got all of that correct. What we missed is the 160 because we didn't think that the isotopes would combine with a different isotope of the same element. Furthermore, we figured out that, okay, the order of the isotopes matters if they're different. So you could have a 7981 and an 8179. So there you go. That is part 3 or step 3. And we're a little bit over, but I'm going to lead you to step 4, okay? Is that all right?
Yes.
Okay, let's go to step 4. So I want to make sure I'm on the right share. So we're looking at the lab. And I'm going to scroll down to, this is Tony's square right here. We just did that. So, and actually, this is still part of, step 4 is my explanation for why step 3 didn't quite turn out great. And you can see this says evaluate. Now we have reasons for the differences. And this first part of step 4 is me trying to explain why you have those differences.
So it's not really a separate step.
No, it is. But, you know, maybe I should put the explanation in below there. But honestly, I wanted you to try and think about the reason for the differences before you read my explanation. Does that make any sense?
Yeah.
Okay, so let's go beyond that explanation and let's go to, so now we can apply what we've learned. Use the simulator to get the mass spectrum of atomic chlorine, report the data table, We don't care about the spectrum, just the data table. And make a guess as to what you think the spectrum is going to look like without doing any calculations of, percentages, just mass. How much will 2 weigh? And then try and draw the peaks based on what we've learned. And then calculate it like we just learned and draw the peaks. So you'll have 2 plots, one where you kind of guess which peak is taller and the other one where you calculate which peak is taller. And then you have 2 hypotheses and you're going to test them. So to help you out with this part, let's go to this the simulator, and let's get the data for chlorine. So you want to write this data down. There's a chlorine 35 that weighs 35, and it's the 100 peak. And there's a chlorine 37 that weighs 32.4. Excuse me, there's a chlorine 37 that weighs 37, and it's only a 32.4 peak. So it's a third the height of the 35. So this is the part where I leave you to your own devices, and you make a qualitative guess where you just kind of get the masses and then figure out which peak is taller based on gut instinct. And then you do the Tony square and you calculate them, and then you test. Let me ask you folks, do you think your qualitative guess will be more correct, or your quantitative where you're calculating things?
Quantitative.
Quantitative, yeah.
Quantitative. Which one do you think is going to be quicker?
Qualitative.
Qualitative.
So why do you think we do a qualitative before we do a quantitative?
Because it's faster.
Easier. Yeah. It would be nice to have an idea of what we think it's going to be. And even when you do the qualitative versus the quantitative, that's like a little hypothesis test. You with me? So I like this lab because you're learning how to make guesses. You're learning how not to be afraid to make guesses. And you're learning how not to be afraid of learning something from your hypotheses, which is what science is all about. So thanks for listening. Do you have any questions you'd like to ask?
I'm sure I will Thursday.
Okay. Thursday, we're going to do another dry lab like this where we'll be talking about formulas of compounds. But I would say one more thing here. The next section is going to be discussion. And your discussion is going to be talking about what you've learned. So you might say things like, well, you know what? I learned that when you're looking at more than one atom, you need to consider all the isotopes, and that isotopes could combine with other isotopes. That what you might think is the largest peak might not be because the order of the isotopes matters. And then you might also say that, but you can make a decent guess from your gut instinct, but doing the calculations really helps. Something like that.
The order of the isotopes, is that, when you say that matters, is that referring to like the Tony square or the Punton square? Is that?
Yeah, let me show you what I mean when I say the order of the isotopes. Okay.
Sounds good. Thank
so
you.
For these 4 squares here, you got a bromine 79 and a bromine 79. Here, you got a bromine 79 and a bromine 81. So you can see I'm starting with these guys.
So the order really is like defines the isotope.
Yeah, and this one is a bromine 81 and a bromine 79. So you see the order is different.
Right, and that based on the order that correlates with the intensity.
Yeah. Okay. So 7981 is different than 8179.
That makes sense.
In other words, when we talk about probabilities, there are two ways of rolling this pair. Two ways. Just kind of like if you want to roll a 7, how many, actually, how do I say this? How many ways are there to roll a 3 when you're playing craps?
2, 3.
Two ways. Two ways.
2 ways.
Because one of the dice could be a 1 and the other one a 2. Or that first dice could be a 2 and the other one a 1. Two ways. So when you're rolling craps, maybe I shouldn't teach you this because now you're going to go to Vegas. So when you look at a 3, you could get a 2 or a 1, or a 1 or a 2. So there's two ways of getting a 3, right? How many ways are there getting a 4? Well, you could get a 1 or a 3, or a 3 or a 1, or a 2 and a 2. So there are 4 ways of rolling a 4. Are you with me there?
Yes.
Oh, I'm sorry, 3 ways. I can't count. How many ways are there getting a 5? A 1 and a 4 and a 1, a 2 and a 3 and a 2, and there's 4 ways of getting a 5. And you can keep progressing this way, right? And when you get how many different ways there are of getting all these different combinations, you find out that if you want to roll a 3, you got 2 chances out of like 36 of rolling a 3. So do you want to bet on 3?
No.
No. And they call 7 craps, so to speak. How many ways if they're rolling a 7? A 1 or a 6 or a 1, a 2 or a 4, a 4 or a 2, a 3 or a 3. Is that all of them?
Two and a 3. Oh, never mind.
Oh, I forgot the other. I got a 4. No, I got them. So there are 5 ways of rolling a 7. If I got this right.
Oh, 3 and a 4.
Oh. Thank you. Not a 4 and a 2, a 3 and a 4.
Or a 3 and a 3. That's
3 and a, there's a 3 and a 4, and there's a 2 and a 5, right? And a 5 and a 2.
Yeah.
there we go.
So we have 1, 2, 3, 4, 5, 6. There's 6 ways of rolling a 7. And a 6, there's a 1 and a 5, 5 and a 1, 2 and a 4, 4 and a 2, and a 3 and a 3. So
Can
there's
you be
5.
my statistics teacher too?
What's that?
Can you be my statistics teacher too?
No. But there's 5 ways of rolling a 6, right?
So 7 in craps is no good, right?
Well, 7, you got, well, we might as well finish this now. 8 is a 1 and a 7, or a 7 and a 1. A 2 and a 6, or a 6 and a 2. A 5 and a 3, or a 3 and a 5. Or actually, there's no 7 on a dice, is there? We better get rid of those. And a 4 and a 4, right?
Good thing we're not paying you for craps lessons.
So there's 1, 2, there's 5 ways of getting an 8. And for a 9, you could get what, a 2 and a 3 and a 5, 3 and a 6, or a 6 and a 3, or a 5 and a 4, and a 4 and a 5. So there's 4 ways of rolling a 9. For a 10, there's basically a 5 and a 5, or a 4 and a 6, and a 6 and a 4. So there's 3 ways. And 11, you can get a 6 and a 5, or a 5 and a 6. So there's 2 ways. And a 12, there's only 1 way, a 6 and a 6. So if we add these all up, 2 plus 3 is 5, plus 5 is 10, 14, 20, 26. What's 26 plus 9 is 35. So I'm wrong about 36, it's 35. So out of all of these, what are the odds, the best odds for rolling something? It's a 7, because you got a 6 out of 35 odds of rolling a 7. You've only got a 5 out of 35 of rolling an 8. So this is when you roll craps, chances are you're not going to roll a 7. You only got a 6 out of 35 of rolling a 7. But if you roll a 7 out of the gate, they call it craps, you lose your hand. But if you roll an 8, that's the point. And the idea is you keep rolling until you get a 7 or until you get an 8 again. What are you more likely to get, an 8 or a 7? Well, a 7, because you got 6 out of 35 chances of rolling a 7 and only a 5 of getting an 8. So chances are you're going to get a 7 before you get an 8. And if you get a 7 before you 8, you lose again. So 7 is like the worst thing to roll. So it's something similar with the isotopes. So bring it back to chemistry, Tony. So there's a bromine 79 and a bromine 81, or you could get a bromine 81 and a bromine 79. But you'll notice here, there's only one way to roll a 2-2. They both have to be 2s, or a 3-3. They both have to be 3s. So I don't know if that makes you feel a little bit better about what we were doing there, but we were basically playing craps. Okay, so maybe instead of Tony's square, I should call this the crap square.
I'd stick with Tony's square.
Yeah. But what if I called it the craps table instead of Tony's square? The craps table.
Tony's scraps.
You don't want to call it Tony's crap. You could call it the chemistry craps table. But that's what we're doing. And probability is just a really fascinating subject. They teach whole classes on it. People major in it. It's really numerical, and you got to have the right mind for it. I don't.
I don't either.
Yeah. I'm not big on stats there, Charlotte.
I don't like it.
I understand a little bit of it, just enough to get into trouble. Okay,
Wow.
people. Thank you for attending today. I appreciate it. I hope you learned something, and tomorrow we'll be back to lectures, and Thursday will be about formulas of compounds and names of compounds. Okay?
Excellent. Thank you.
Bye.
All right. Have a good rest of your day.
You too.